of Medicine in Seattle. This is a fireside chat, literally, on what to do about our climate problem. It's not really my favorite subject. Favorite subject would be how human evolution was affected by abrupt climate shifts in the past, in the ice ages, when we were acquiring our abilities for things like language and planning ahead. But paying attention to this for the last 30 years has also given me a ringside seat for the developments in climate science that show us what's likely to happen to our civilization unless we act swiftly to counter global warming. I'm a great fan of the climate scientists. They've certainly done a magnificent scientific job. But they didn't aspire to be climate doctors. No one did. They, like the rest of us, are just winging it when it comes to anticipating climate-generated emergencies. For physicians, the window of opportunity for intervening successfully in a disease has become part of their training. They know how fleeting an opportunity can be, that the clock is always running. Though I'm not a physician, you can't hang around the medical school for 50 years now without absorbing some of that way of thinking and noticing its almost complete absence from our climate agenda, both out of the climate scientists and of the public discussion. So, I'm going to offer you a second opinion about the climate diagnosis, the prognosis if left untreated, and what treatments might actually fix the climate problem rather than merely delaying civilization's collapse by a few more decades. It's sobering stuff, but our situation turns out not to be hopeless at all. We may still retrieve the climate that we used to have at the cost of the economy can afford. You know? That's Mount Rainier, the way it currently appears, seen from Seattle, looking over Lake Union. And this shows what it will look like after a few more decades. All the glaciers in the world, the mountain glaciers, are predicted to lose their permanent ice. So at the end of the summer, they're going to look a bit like this. So let me review briefly the cause and effects of our global warming problem. First of all, fossil fuel burning, cutting down forests without replanting, and letting peat bogs rot and the permafrost melt and rot. All those are amongst the things that increase the greenhouse gases in the air, primarily CO2. Now, the effects of this increased CO2 in the air, we currently have about a 40% excess, are ocean acidification, and the greenhouse effect produces a global overheating. Global warming sounds altogether too warm and fuzzy. Overheating or fever would be a much more appropriate term. What that in turn causes, of course, are warmer winters and all the insect infestations that will come with it without a good freeze to kill off the larvae. We'll have more extreme weather of various sorts, higher winds, heat waves, of course, deluge and drought, which often go together. When the currents of moist air that come off the oceans change direction, the region that they were headed for originally gets drought, and the region they go to gets deluge. Of course, deluge and drought tend to lead to flood and to famine. The third general category is that you get a permanent drought, if you like, as the tropics expand, because the deserts start marching away from the equator. For example, the Sahara's climate winds up impinging upon the Mediterranean. The southern European countries like Spain, Italy, Greece are already having significant problems with drought. And finally, the effect of global overheating is that we're getting more and more climate instability. I'm going to talk about it quite a bit more in a minute. Now let's discuss what the climate agenda was back in the 1970s when we first started talking about this. So this is the 1970s version of the climate diagnosis, CO2 poisoning. The prognosis, it's going to slowly warm up, and the intervention needed, reduce emissions. Nothing's changed. That's still what the public discussion and the climate science position and policy wonks position. And by now, it's quite inadequate. There were some important questions that have been answered, however, since the 1970s. The questions back there, is it really warming? And back in the 1970s, that was not so clear. It turns out that there was not really much of a trend between 1950 and 1976. Apparently something was countering the greenhouse effect back then, something the equivalent of air conditioning, countering the warming in this room from the fireplace. When the air conditioning effect reaches its maximum, because that's only how powerful the air conditioner is, then the temperature starts going up. And something like that may well have happened back in 1976. The other important questions, won't warming and more CO2 be good for agriculture? And the answer to that hasn't been clear until the last decade or so. There have been good experiments showing that whatever good there is for certain crops and certain climates, it turns into a negative by 1 degree of warming. And there are questions like, are you really, really sure? Well, climate scientists have to admit, like all scientists, of course, that, you can't be really sure. Something might happen that will change your view of things. That's the position that scientists in all fields tend to take. And so if you're a lobbyist trying to slow down this whole business of doing something about climate change, that's one of the things they keep harping on over and over. And, of course, a physician that would have to point out to a patient who keeps asking that is that, the physician who waits until dead certain about a diagnosis is likely to wind up with a dead patient. Then there's the question of, but that's so next century. That's what they said back in the 20th century. And that's what we're saying in the 21st century about, it's 22nd century. Something's going to happen. Well, lots of things have changed since the 70s. We're all about 40 years older now. Technology, of course, has changed quite a lot. Slide rules used to rule the day until the HP 35 scientific calculator came in about 1972 or so. It has certainly been improved over, the last 40 years or so. It now has a better display, a much better keyboard, things like that. In fact, it's almost gotten to be such that be one of those fetishes that you dangle from your rearview mirror. But of course, that's really because it's also a video phone, so you have face-to-face conversations with people now while you're crossing the street and not watching the traffic. If you're not sure where you're going, it's got a built-in compass, and if that's not good enough for you, it's got a built-in GPS too. And it will send short messages, it will guide you to your destination. If you're driving in circles, it will help adjudicate disputes about whether you're driving in a circle or not by showing you the track you've been on. Well, climate has changed quite a bit since the 1970s. The way I would formulate the diagnosis, prognosis, etc. now would look like this. Yes, it's CO2 poisoning with secondary effects of climate instability and ocean acidification. Prognosis, yeah, there's a warming trend, but sudden climate shifts atop it, sometimes big enough to cause the famine and population movements that are associated with the big population crash, 9 billion people. The intervention needed is not just reducing emissions, it is now removing the excess CO2 from the air. So here's just a reminder of what high winds can do, but I want to remind you about what the insurance companies know about the difference between a 50-mile-an-hour windstorm and a 60-mile-an-hour windstorm. That's only a 20% increase in wind speed, but the damage doesn't go up 20%. It doesn't even go up 50%. It goes up about 500%. And that's just the insurance company's loss records that tell you this. So there's a lot of very non-linear stuff in this. And a lot of it is because of cascading damage. That is to say, something that's blown off a building for a 50-mile wind may hit the ground and bounce along before it ever runs into another building. But 60 miles an hour, some of it will manage to hit another building and knock something loose from it before it hits the ground. So cascading damage is something that is hard to estimate, but is certainly, even if it's hard to estimate, you have to figure there's going to be a lot of cascading damage. So let's now talk about emissions. And my first caution to you is that a lot of people think emissions are all that excess CO2 in the atmosphere, 40% increase in CO2 concentration. But once things are plotted, it's always plotted as an annual rate of addition to that accumulation. That is to say, there's sort of a double standard in using the word emissions, and this has confused quite a lot of people, I think. What's shown here is sort of the way the annual CO2 production has been going. We were down around 1.6 gigatons of carbon in 1950 being emitted as fossil fuels. Then it grew about threefold in the 70s and 80s. Here we are now at about 9 gigatons. And during all this period, going back to 1750, at the beginning of the Industrial Revolution, about 350 gigatons were emitted. But during the next 2 decades, next 20 years here, we expect another 250 to be emitted if we continue having a 3% annual growth in emissions rate. Okay? So our overall problem, assuming we can try to fix it in 20 years, is getting rid of 600 gigatons of carbon out of the atmospheric circulation. Stabilizing emissions, stabilizing is a terrible word because it has no implications about stabilizing climate to it at all. It just means flattening the curve. That does not reduce accumulation. Zeroing the emissions still doesn't reduce accumulation. So basically, all of this should have been pretty obvious, even back in the mid-1990s, at the time of the Kyoto Accords. It was pretty clear then that developing countries are even less likely to control their use of fossil fuels than the developed countries that have mostly failed to do so. So we really ought to expect them to continue to burn their own fossil fuels in order to generate electricity to modernize like us. We have to do something to counter those emissions rather than just trying to get them to not be emitted. The other thing that's been pretty obvious for the last 5 years is that from the climate models that have been done of how much it will warm up, it's pretty clear that even our most ambitious scenarios for reducing emissions and slowing economic growth don't serve to delay a 2-degree overheating very much. From 2049 to 2068, a mere 19 years is all you gain this way. So it should be pretty obvious that if we continue playing this game of pretending that we're going to reduce emissions, that we are in for a disaster. Furthermore, if we were to achieve zero emissions, even 1,000 years later, about 1/4 of the excess CO2 would still be up in the air. Reducing emissions doesn't reduce this ocean acidification anytime soon, nor does it reduce the chance of an abrupt climate shift. The other thing is that we're getting into the area of vicious cycles, things that take off and run on their own no matter what we do. We're beginning to uncork the CO2 and the methane that can be produced by the Arctic tundra as it thaws. The Arctic tundra is very compact organic matter that is never decomposed yet. Being frozen, it doesn't do so. Once it thaws, you get CO2, and as the oxygen runs out in the depths, you get methane produced primarily instead. That is a vicious cycle. The overheating yields more CO2 and methane, therefore even more overheating, therefore even more overheating. So, if you haven't seen permafrost, here's an example of what looks like in Siberia. These are basically frozen peat bogs.
It is a very potent greenhouse gas. The molecule of methane is 25 times stronger than methane is formed in billions of lakes around the Arctic where permafrost is thawing. And each year, these lakes are getting running tremendous amounts of methane. When we look at how much carbon is in permafrost still frozen, the potential for that permafrost to thaw in the future, we estimate that more than 10 times the amount of methane that's right now in the atmosphere will come out of these lakes.
So if that's our situation, what are we going to do about it? The usual response to this is change the topic, because it's not clear what we can do about it. But I think it's important to analyze a worst-case scenario so that you can discover how to head it off in time. We're not very good at this. Banking and Wall Street regulators should have been planning for how to act if a housing bubble bursted, etc. And it turns out they were relying on crossed fingers instead. We can't afford to do that for climate. The anthropologists show that most societies of the past have collapsed. And prolonged drought was really their leading cause of death. Jared Diamond analyzed 22 societies that fought with collapse. Some staved it off. Most did not. We, on the other hand, have a lot of science and we have a lot of technology. And hopefully we have a bit more wisdom from learning from history. But our current agenda, based on that 1970s view of the situation, really looks more like a buying time therapy for late-stage cancer. Certainly, it's not looking like a physiological fix that makes possible a near-normal patient, such as the dialysis for kidney failure, which gives those patients a near-normal life. Our current climate response is really mostly a re-emphasis of the old virtues of clean air, clean energy, sustainable agriculture, reforestation, greater efficiency, less waste, longer-term thinking. How can you disagree with this? But few of those will help us quickly recover from our current 40% excess of CO2. Furthermore, this agenda has not gone unnoticed. The Deny and Delay Squad, magnificently funded by the fossil fuel industry, suggests that all of this is just green activism and new clothing. So they are suggesting to us we can really ignore the problem if we don't agree with the green agenda. Unfortunately, that's not going to make anything go away. The problem is that we need, in addition to all of this, we need to quickly recover the 40% excess of CO2. So our current situation looks a lot like locking the barn door after the horse is gone. It's not likely to recover the horse, though giving the appearance of taking action. Even zeroing emissions is only going to delay collapse, I think, by a couple of decades. You have to actually remove the excess CO2 to fix the climate problems and get back to normal. We really don't have time left after 60 years of fiddling around, to do things like major social engineering or major research breakthroughs. What was reasonable in the 1970s is not enough now, given the interim CO2 accumulation and the climate problems that have already appeared. Several analogies, if you like. Brushing your teeth more regularly is not a fix for a cavity that is already developed. To speak only of emissions reduction these days is like preaching fire prevention for the four-alarm fire down the block, already burning. So Wile E. Coyote does represent a situation that we are in. Now it looks like we have already ventured beyond terra firma, and that our climate agenda won't support us. Now compare this to what a serious solution to the climate problem would do. Putting past emissions back into secure storage would reduce the global temperature, relieve deluge and drought, reverse ocean acidification, reverse half of the sea level rise, part due to thermal expansion as the oceans cool, and reduce the chance of abrupt climate shifts. What's the time frame we have to do this in? Well, it depends on how long you're willing to wait. How long until the global economy collapses? How long until life becomes cheap? Climate refugees everywhere trying to go places where there's no room and no food for them. And how long, of course, is it until an abrupt climate shift that speeds up both of them? I can't predict that future for you, but I can tell you the time scale of other abrupt climate shifts that have been like minor heart attacks. Here are some major heart attack versions of it. During the last ice age, here is our warm period. This is the last 10,000 years in which agricultural civilizations have been around. Homo sapiens, our species, has been around for about twice the length of this, back 200,000 years. The last warm period in the Ice Age is back around 120,000 years ago. And what you see here is, this is a temperature proxy, but basically this is our current average temperature. And it's what's called a warm and wet climate. Ice Age climates are cool, dry, windy, dusty. And what this graph shows you is that the Ice Ages were not some gradual roller coaster of warming and cooling. Once you look at the high-resolution records, which you get from Greenland and Antarctic ice cores, you see that there were really fast excursions. For example, here's a fast excursion that goes down in 10 or 20 years, and the fast excursions up, in some cases, are less than 1 or 2 years. So these are abrupt climate changes in temperature. They are also just as abrupt if you measure other things. If you measure rainfall, if you measure the amount of dust in the atmosphere, if you measure how windy it is, all of those things change suddenly as temperature changes as well. Now, it turns out that we, in our current time, this last generation or two of us, have been experiencing some abrupt climate shifts. They're not of this classic kind of evolving temperature, but they certainly appear using drought. Since 1976, we've had quite a few of them. And the importance here is that even though they might be smaller than the classic ones in the past, civilization is now pretty overextended at 9 billion. And half of us now live in big cities at the end of a long supply line. And in a famine, the food will disappear before it ever reaches the city. So the result of a modern abrupt shift could be catastrophic, even with much smaller abrupt climate shifts. So the overall total since '76, there have been about 6 abrupt climate shifts, global in extent. There are a lot more that are regional, but the global ones number 6. And at least 6 near misses. Now 6 plus 6, 12 years in 35 as a track record. Not computer forecasts, but that record is why we now need CO2 cleanup that is big and is quick. So let me show you 3 of the abrupt shifts. This shows you a plot in time of world drought. Here's 1950, 60, 70, 80. So during this period, about 14% of the world's land surface was in the kind of severe drought that Texas has been in. That is to say, about 1 acre in every 7 around the world has been in severe drought, and that's just the normal sort of baseline kind of activity. What's in drought, particular regions move around from year to year, but overall it's been about 1 in 7 acres. In 1982, it changed. That is to say, it doubled, all within 1 year. Now that year, 1982, a couple of other significant things happened, and there's a tendency to think they were the cause of it. There was a big volcanic eruption, the El Chajun eruption, and there was also a big El Nino, biggest one ever seen at that time. Now, both of those were sort of over and done with within a year or 2, but the drought did not come back down. So during this next 15 years, when there are various El Ninos and La Ninas coming and going, drought stayed up and doubled. So we are now in an area where it's sort of like flicking a light switch and popping into a new mode of operation, or like a gear shift for a car, if you like. Because, you know, shifting from first to second and then into high gear with the 1997 eruption, popped up from double to triple for about 8 years and then shifted back down into the range of double in 2005. So that's the kind of thing that you have to keep in mind when you're looking at the climate of the future. It's not necessarily going to gradually change. In fact, if anything, climate tends to take leaps rather than just shuffle along. Now, one thing to note here is that CO2 accumulation wasn't doing this, it was gradual. Yet the climate mechanisms responded with sudden shifts. The other 3 sudden shifts take a lot of time to describe because they're from oceanography. But let's take a look at 3 of the half dozen near misses that I've identified in the period following 1976. Back before 1997, we assumed that rainforests couldn't burn. After all, they were sodden with rain. You know, how on earth could you ever get a forest fire going? Then the rainforests in both Amazonia and Southeast Asia dried enough during the really big El Nino that year so that large areas burned. And the areas that didn't burn were surrounded by areas that were still so dry they killed a lot of trees. And so those trees rot, putting CO2 in the atmosphere just as sure as fire does, just more slowly. So the question you've got to ask, and which I frankly have never seen anyone ask, is what if the biggest El Nino had lasted 2 years rather than just 1? They certainly can last longer, they just haven't been that big. There was an El Nino that lasted from 2001 through 2005. But this caution of mine is coming over superseded now because even without a big El Nino since 97, the Amazon has become extremely dry. This is the western Amazon with a drought just as bad as Texas. 2005 and again in 2010, Amazonia was even more flammable than it was during that one-year big El Nino in 1997. And once we lose this particular rainforest, the Amazon, it doesn't grow back. Plant cessation will stay stuck at grass for a very long time. That is to say, it won't recover much of the CO2 that was vented into the air by the fire and rotting. So essentially, this is an irreversible addition of CO2 to the atmospheric circulation. So thanks to rainforest burning, you could also have jumps in the excess CO2 causing jumps in climate with all the same CO2 mixes in just a couple of years worldwide. And so worldwide, you would expect a sudden intensification of those standard consequences of overheating, heat waves, outbreaks of disease, deluge and drought, tropics and deserts expanding. And of course, it would also be a mass extinction event. That is to say, I asked Ed Wilson what he thought how many species would be killed off, go extinct, if we had an event like this. And he said that within 100 years, he really expected about half of them would go extinct. If it hits the rainforest of Southeast Asia, it will also take 3 of our closest relatives in the animal kingdom with it. So if climate creep, what we have been discussing before now, is like a slow motion train wreck, and climate leap is like a heart attack. It comes as a surprise, and since you don't know in advance if it's going to be minor or catastrophic, the imperative is to prevent it. As those drought steps show, that is a totally inadequate way of framing our climate problem and tasks facing us. It's business about climate creep and emissions reduction. Abrupt climate shifts are both sudden and severe. They're like heart attacks in 3 ways. You can't predict when, you can't predict if the next one's going to be minor or catastrophic. Catastrophic could mean a human population crash. And 3, only prevention works. Well, the 1970s version of what to do about it is still pretty much the public agenda today. The action proposals focus on mitigation. Now, that's a bureaucratic word for softening the blow. In other words, if you fall out a window, somebody puts a mattress underneath where you're going to land to try to soften the blow. This may not keep you from getting killed, might buy you a little bit of extra time. Besides mitigation, there's also adaptation. I like to joke this will literally make us troglodytes as we try to live in caves where it's cooler. But the most common way of living where it's cooler would be to move to a higher latitude. So flee the tropical countries for the temperature. This is already beginning. The Europeans are already concerned about the wave of immigration from the Sahara countries. Seldom mentioned, even by the climate scientists these days, is the third obvious action. Actually repairing the climate itself and thereby backing out of the dangers. So in addition to a low-carbon diet, we need emergency repairs. And that's an intervention rather like dialysis. Quickly cleans out the toxic substances. Judging from the rate at which climate surprises have been occurring, we may only have several decades remaining for an effective intervention. That's the time for completing repairs, not that for getting started. Because we would expect about 6 abrupt shifts or near misses in the next 20 years if the previous 30 years is anything to judge from. Yet, top climate scientists, at least two of them, have said almost exactly these words. Techniques for extracting atmospheric CO2 might eventually prove necessary, as if there were no real urgency about reburying fossil CO2. Now, admittedly, our task is daunting. It's really a matter of putting the genie back in the bottle, removing nearly all of that excess CO2 and putting it back into long-term storage where it can't circulate in the air anymore. Here is the emissions record. And let me start by cautioning you that emissions, when you get right down to it, usually means a rate. It's like miles per hour. It's the amount of carbon emitted, the amount of excess carbon dioxide emitted into the air in a one-year period. A lot of people confuse this with the accumulation in the atmosphere. It is certainly the result of emissions, but it's like confusing miles with miles per hour. So here's what we need to do in order to remove stuff on the time scale I'm talking about. If we want to counter all of that CO2 emissions, we have to do things like this. We have to, first of all, capture enough CO2 so that we cancel out the continuing emissions, that 3% growth. And we have to go beyond that and sink all the past emissions. That will take about 34 gigatons per year over 20 years now. And it will just get worse with additional delay. So what are the ways of taking CO2 out of the air? The long-term one is weathering rock. It's essentially acid rain, carbonic acid rather than sulfuric acid. And it's far too slow for us to consider. There are, of course, scrubber machines like submarines use when they're recirculating the air. They take CO2 out of them with caustic chemicals, usually. Doing that on an atmosphere-wide scale, of course, would need an enormous amount of new electrical power to do it with, and it'd have to be clean electrical power to do it. While we perhaps could get there eventually, this is not quick. Or photosynthesis. That is to say, beyond the amount we have now of having a lot more photosynthesis for 20 years. Now, how do you do that? Freeman Dyson pointed out back in 1977 that grow more forests, obviously. And it is convenient that the forests of the world are about 600 gigatons, and that's about the amount we have to take out. So doubling forests would conceivably do the job. But even if space and water can be found for this doubling of forests, the climate forecast is for more drought and more high wind, making new forests insufficiently secure against fire and rot. I mean, we can't even keep rainforests from burning now. So this solution, I think, has become a non-starter. To avoid competing towards food production, you'd better stay away from things that involve land and water on land. And that pretty well says you've got to grow your new biomass in new places if you're going to do it quickly. For example, sinking additional cell debris into the ocean depths via fertilizing the algae. So let's look at that. Only algae has the needed growing space anymore. But the requirement is not only growing it, but then sinking enough of the new algae each year into the ocean depths to equal the 34 tons a year. So I'm going to have to tell you a little bit about how CO2 has been taken out of the oceans, taken out of the air already by the oceans, about 100 gigatons so far, and 350 cumulative emissions since 1750. The method I'm going to propose involves ocean pipes, but we'll get to that in a second. So here's just a schematic diagram. Down here at the bottom is the bottom of the ocean, where sediment piles up very slowly. Here's the surface, and here's just a box diagram of the atmosphere. It's having carbon added to it by deforestation without replacement at about 2 gigatons a year. And fossil fuels and cement are currently adding about 9. It interacts, of course, with the vegetation and soils of rock on land, and with that in the oceans. The oceans is currently absorbing about 92 gigatons of CO2, but it's emitting back in the atmosphere about 90. So it's only about a 2 gigaton gain. Now, the ocean is subdivided into a bottom, the depths of the ocean, and a surface layer which is defined by being well mixed. Say the winds cause waves, and the waves cause mixing into a depths a certain distance, depending on how strong the winds are. When the winds are really strong, it can go down a lot further than 100 meters, but it's about 30 meters over the continental shelves. 100 is sort of a nice round. However, the ocean depths now contain 98% of the ocean volume, and this is a slow circulation. This does come back up to the surface eventually, but eventually is like 1,000 years. And the carbon dioxide may come up even more slowly. So the black boxes in the middle of this just show you the plankton production. Plankton is algae, phytoplankton. And then zooplankton is all the little animals that eat. They graze on algae, and they're mostly microscopic. Of course, it's one of these big fish, eat the little fish kind of things, and the whole food chain, really runs on what at the bottom is photosynthesis by the algae. Okay, now of this product here, plankton take in about 48 and put out about 37 by rotting when they die, and by respiration while they're living. Respiration is the whole point of photosynthesis, because algae have to live through the night when there's no sunlight to stoke them. And we get a nice part of the bargain that way, because they, as they photosynthesize, they cleave off the oxygen from the carbon dioxide, and it goes back into the air as oxygen. Now, the difference between these, 11 gigatons, is what manages to settle into the slow-moving ocean depths. And it mostly settles down because it's big enough to fall rapidly. It doesn't stay suspended in the surface ocean. It falls. And only the bigger fecal pellets and some of the bigger cell debris can fall that far without coming apart and becoming so small that they don't sink anymore, and becoming part of this 90 gigatons a year that's released back. So that's the general scale of this, what's called the carbon cycle. Now, let's look at how we could augment it. If we were to fertilize the plankton production by providing additional nutrients, it's by no means operating at its highest rate. So you can jazz this up, but you have to jazz it up 3-fold to 4-fold the total by fertilization in order to get an amount sufficient to do that 34 or so gigatons a year. Fertilizing the 70% of the Earth's surface that is ocean to 4-fold production, and doing it quickly without complications. This is not going to be the way we do it. So let's look at other ways. In addition to settling out debris and fecal pellets, there is the carbon that's carried along by currents, by bulk flow, as we say in physiology, by convection, as the oceanographers call it. Whirlpools move both inorganic and organic carbon into the more secure depths. The estimates for them resurfacing range from 4 to 1,600 years or so. So let's think about pumps. If we put a pump in and took the surface water, not just the plankton, but all the surface water, and pump it down into the deep ocean, and pump it in a quantity that would suffice. So we want to sink at least 30 gigatons. It's 31 to start with, so we're talking about doubling it overall. Now, pumping the welling water back up to the surface and having it go down in whirlpools the way it normally does, that's where this descending current comes from, is typically big whirlpools. They're up near Greenland, either in the northeast ocean off the northeast of Greenland in the Greenland Sea, or off the southwest corner of Greenland down in the Labrador Sea. That's where most of the sinking is done. There's about 10% of it that's done near Antarctica by a different mechanism. But those areas are the critical ones for maintaining this downwards flow. So overall, it looks like this. And I would point out that this is analogous to the farmer's cover crop. Back in the old days, without fertilizer, what farmers used to do is to leave the field unproductive for a year, but to cover it with a crop of beans, clover, something that takes a lot of nitrogen out of the air and buries it in the soil so that plant growth the next year of your crop that you want will have it to work under. So in this case, what we're doing is we're plowing under the production of the surface ocean that's been stimulated, and we're burying it in the deep ocean. Now, there are several ways to run these long pipe pumps. All schemes like this are going to have a pipe that goes down below the thermocline. So that'd be, if this is 30 meters on the continental shelf, this would be a 50-meter pipe, or a 100-meter pipe. A 100-meter pipe is about like a 30-story building. The question is how you power those pipes. Obviously, with a windmill type arrangement, the old-fashioned farmer's windmill, mind you, but with modern new rotor blades, you can either pump up or down, depending on how you set the pump. There's some cheaper ways of doing this, with wind power secondarily in the form of waves. The wind generates waves that go up and down, and they can be used to pull water up from the depths or to push it down. Here's a push it down thing. You have an open pipe, except it's got a trapdoor valve at one end. And as the buoy is pulling the pipe up from the depths, it extrudes water that used to be up at the surface. And then when the crest of the wave develops and it goes down, trapdoor closes and it goes down, and then it goes up again, the thing opens. That's how this pump gets primed and how it continues to work, as long as there are waves to run it. So that's a very cheap way of creating these pumps. What a plankton plantation, as I like to call them, would look like, I'll illustrate with the windmills, simply because they're more visually attractive than buoys. Here would be pumps that were set to pump nutrients up, and the current carries these nutrients across the space here, where there's a big bloom of plankton going on. And then down here, you have a row of pumps that are basically pumping downwards. So in contrast to ocean pipes just for bringing nutrients up, we now have what's called a push-pull pump. There's as common in physiology labs as vacuum pumps are in physics labs. So this is what I'm suggesting is the great unexplored opportunity for climate. I'm throwing a fishing lane in here because, of course, we won't succeed in sinking all of the new plankton production, fish will come in and eat it. And so we may as well let the fishermen try to harvest this excess of fish. The world's oceans have had their fish supply reduced 73%, even if with sustainable harvesting. In other words, that's what sustainable means, is keeping it from going no lower than 27%. So that also meets a great need. I'm showing additional rows back here. The question is now, how much of the ocean's surface do you have to do this in? Is it the whole ocean again? Well, here's the back of the envelope calculation that I've done on this, using figures for algal stimulated growth that come from basically the biodiesel efforts of the 1990s. Show that you need about 1% of the world's ocean surface as plankton plantations. You know, it's an area about, the Caribbean is about 0.8%. And that's about what you need. But you wouldn't want to do it in the Caribbean. You'd want to do it probably on the continental shelves, well out from shore near the drop-off in depths. The least expensive pumps are these wave-powered ones that bob up and down, and the inventor of those, invented for other purposes, I might note, are about $1,000 each deployed. 1 million of them would therefore cost about $1 billion US. Well, can we afford it? I mean, $1 billion is what Americans spend on dog food, and in only 1 month. We're talking about 1 billion over 20 years. But it's, of course, best to figure it's going to cost more than that, 10 times, 100 times, well, it's 1,000 times more than that. $1 trillion is the price tag for that unbudgeted bank bailout back in 2008. So I think that these kinds of fixes are probably well within our economic means. But let me close by saying that the climate prospects are not good if we don't do something that big by some means that will probably look something like what I've sketched out for you. All it takes is a big climate leap that cripples agriculture long enough for the big cities to crash. And before someone objects that big cities have survived big droughts before, note that this hypothetical famine is global in extent. The usual remedies of the past, importing food or immigrating someplace where there is food, are not going to work in a global case. So a serious jolt would cause catastrophic crop failures and food riots, certainly within a year, probably within a month, creating global waves of climate refugees with all the attendant famine, pestilence, war, and genocide. Political scene currently, and this is just my personal opinion, but current political scene makes you wonder if human wisdom is mature enough yet to avoid committing collective suicide. Even though we're still capable, clearly, both technologically and economically, of repairing the rot we have caused in the foundations. The problem is the political willpower to do it quickly enough. So like the terminal kidney patients that I saw back before dialysis became more widely available, our civilization is starting to look like a goner, apt to trip into a vicious downsizing cycle. But we can fix it. The take-home messages here, there's 3. 1, we need to reframe the problem. It's not just emissions reductions and CO2 accumulation. It's climate instability with potential for climate crash. It's not just a matter of more expensive air conditioning during the summertime. Big sudden problems do the damage before gradual changes can get around to it. Three, it's not hopeless. There are ways to clean up the excess CO2 in 20 years if we light a big enough fire under our politicians. We have the simple technology and currently the economic base to repair climate. The end, well, I hope that's not the end, but it's a good time to stop.